Hello dear students, welcome back to the tetrahedral chemistry classes. And in today class, I am going to discuss another very important aspect of the stereochemistry, which is your Felkin Anh model. If you are following my lecture, then in my last lecture, I have explained the CRAM'S rule, right? And today we will see the comparison between the CRAM'S rules and the Felkin Anh model. But for the students who are watching this video for the first time and want to learn the stereochemistry, so I am telling you these two rules, whether the CRAM'S rule or the Felkin Anh model, they both are used to predict the percentage of the diastereomers during the nucleophilic addition on the carbonyl compound, right? See, in a little while we will see the examples as well. For the background, you should know this particular very important point. When you have the carbonyl compound, right, whether it is aldehyde or the ketone, and this carbonyl compound at the alpha carbon is having the chiral center. So what will happen? One chiral center is already there, and carbonyl compound during this nucleophilic addition will also produce another chiral center. That means your molecule, your product will have the two stereo centers, and you will have the diastereomers, formation of the diastereomers. And of course, the one diastereomers would form in the major amount, and the other one would form in the minor amount, right? This is the whole idea about the nucleophilic addition reactions and the stereochemistry of the nucleophilic addition reactions. And for this, I have explained this this CRAM'S rule in a pretty much detail in my last lecture. Okay, so what you can do, I am giving you the link in the description box. You can go there and see how we can apply the CRAM'S rule in the nucleophilic addition reactions. Okay. And today I'll discuss another very important model, which is the Felkin Anh model, which is a little bit superior than the CRAM'S model, because there are certain cases or certain reactions where the CRAM'S rule does not predict the diastereomers percentage correctly or accurately, right? It fails basically. So we'll use the Felkin Anh model, which is little bit more fundamental than the CRAM'S rule. First of all, we should know the difference between the two. So please remember, your CRAM'S rule is a qualitative approach. Okay, so it will only tell you that the particular diastereomer will form in the higher amount, and there is no prediction of the exact percentages. Okay, but this Felkin Anh model or Felkin Anh approach, which is supported by the quantum chemistry or the quantum mechanics, right? So it is the more fundamental one, and it will give you the quantitative idea as well. That means if you are forming a two diastereomers, what percentage of the diastereomers would be there? Say the one is 81%, other one is 19%. So this idea you can have by using the Felkin Anh model. However, it is based on the rigorous quantum mechanical calculations. So we'll not cover that quantitative aspect here, but you should know that it is quantitative in nature. This is the first point of the differentiation between the two models. Okay. Now the point number two, less accurate predictions of the diastereoselectivity, as I already told you. Okay, but here you will get the more accurate predictions of the stereochemistry. And the third point of differentiation is that a CRAM'S rule only assumes that the largest group has anti-periplanar relationship with the carbonyl group, right? Say this is your carbonyl compound. Okay, and this is the this is aldehyde, right? This is H, and this is the rear carbon. When this will happen, so your R medium group and your R small group would be there, and your large group will almost have a eclipsed conformation with this hydrogen. Okay, that means your carbonyl group will always rest between the medium and the smaller group in the CRAM'S model. Okay, this I have explained, right? You can go there in my lecture and understand this thing as well. But in the Felkin Anh model, largest group is perpendicular to the carbonyl group. Here you can see the larger group is basically what it is almost anti-periplanar, right? But in the Felkin Anh model, largest group will occupy the position which would be the perpendicular to the plane of the carbonyl group, and of course anti to the incoming nucleophile, because we are doing the nucleophilic addition to this particular reaction. So it is not enough that your largest group would be anti to the carbonyl group, but it is also required that this largest group must have the anti relationship with respect to the incoming nucleophile. So the repulsion decreases and the rate of the reaction increases, and you will get the higher diastereomeric percentages of a particular diastereomers. Right. This is the third point of the differentiation. Now the point number 4. This CRAM'S rule only gives the importance to the groups attached to the prochiral center. That means, see, this is the prochiral center, right? And it has attached with this real carbon is the prochiral center. If these RM, RS, and RL are different, so only these three groups have the have noticed by the CRAM'S only, right? And but in case of the Felkin Anh model, it gives the importance to both the groups which are attached to the prochiral carbon as well as to the incoming nucleophile. See, size of the nucleophile again plays a very important role in the nucleophilic addition reactions, but CRAM'S rule completely ignores the size of the nucleophile, and Felkin Anh model gives emphasis to the size of the nucleophile as well. That's why it is giving the more accurate prediction of the diastereomers percentages, right? And CRAM'S rule does have the very limited applications. At times it fails actually, but you see this Felkin Anh model applied to the wider range of the reactions, including those reactions as well which involves the large nucleophile and the carbonyl compounds are very complex. See, this CRAM'S rule is applicable only for the simple carbonyl compounds, but when you have the complex carbonyl compound, then this CRAM'S rule fails in predicting the diastereomeric percentages, okay, or the major or the minor nature of the diastereomers. It gives error, but Felkin Anh model gives the accurate results whether their carbonyl compound is simple or the complex one, and also how actually larger nucleophile and the smaller nucleophile affects the rate of the reaction and the diastereomeric percentages. This can also be explained on the basis of the Felkin Anh model. This is the important difference, right? You should know this thing. Okay. Now, let us check how we can understand the thing. This group is your small group. This is your medium group, and this is your large group. And in the center, you are having the carbon, and this carbon is connected with the carbonyl carbon here. And say this is your alkyl group R. Okay. So this is the medium group, this is the small group, this is the large group. Okay. And you are viewing your molecule from this particular direction. That means this carbon is the front carbon, this carbon is the rear carbon. So how we can draw the conformation? So what Felkin says that, right? Felkin said that you can draw the conformation in that manner. This is your this front carbon, which is this one, the chiral one, okay? Prochiral center is there, and it is having this group S. So I am putting S here, and then I am putting M here, and then I am putting L here. There is no problem in that because I view the molecule from this particular direction. So this is by chiral carbon, and this is by M, which is this one medium group. This is by S, which is the smaller group, and this is L, which is just like that. And this is your rear carbon. The carbonyl carbon is the rear carbon, and I am drawing my rear carbon. And you know that in the stereochemistry, in the Newman projection formula, this rear carbon is always shown by the this circle actually. Okay, and then I am placing this double bond oxygen to it. So this is my double bond oxygen, just like that. And anti to this, you are having this group R. This is the one conformer. Okay. So what Felkin says that whenever you have the large group, it will form a orthogonal relationship to the carbonyl carbon. That means it will be placed perpendicular to the plane of the carbonyl carbon. That means this angle is the 90 degree. So this is one conformer. Please remember, this is one conformer. And what you can do here, right? I can fix the position of the rear carbon, and I can rotate my front carbon. Okay, if I rotate my front carbon by 180 degree, so I am writing here 180 degree rotation of front carbon. So you know this center one is the front carbon. If I rotate this by 180 degree, what will happen? This L will come here after 180 degree rotation. This M will go down, and this S will go up, and we will have another conformer for this one. So how that conformer will look like. So first of all, I am drawing my this carbonyl group and the R, because I have fixed the position of this one and only rotating the front carbon. Okay. So what will happen? This will come here. So this is where large group. This will go up. This is where smaller group, and this will come down. This is where medium group. See, I have rotated this thing actually, right? So this will come here, this will come here, and this will go there. So this is another conformer, right? These are the two very, very important conformers. Okay. And you see this larger group is placed perpendicular to this one, as well as in the second example, right? This is again placed at the 90 degree to the plane of the carbonyl group. So these are the two forms actually. And what Felkin says that it is supported by the quantum mechanics. Say it is A and it is B. Okay. So it was found that these two conformers, which was actually assumed by the Felkin, they are energetically same. Right? They are the most favored one, and they are energetically similar. That means their stability is roughly same. There is no difference in them. Right? But when the nucleophile will attack on this rear carbonyl carbon during the nucleophilic addition reaction, then there occurs some sort of the repulsion. So how you can see, I'm giving you the example here. Say my nucleophile in the first conformer, my nucleophile is approaching onto this rear carbon from this particular direction. I'm writing nucleophile here. Okay. So what is happening here? You see, this group is small and this group is medium. So you see there is no repulsion between the nucleophile and the smaller group. So this is not a this small group will not actually create much difficulty to the nucleophile to approach onto this particular carbon atom. Okay. Now in the second step, what you can do, say your next approach is what? Your this nucleophile is approaching towards this carbon atom from this particular direction. So you see here, this group is medium. So there would be repulsion between this medium-sized group and the nucleophile. However, this repulsion is not there in that case because this group is a small one. However, in both the cases, you see, nucleophile is approaching onto this carbon just opposite to that of your larger group, and it attacks to the Burgi-Dunist angle. Please remember Burgi-Dunist trajectory, roughly 107 degrees. So this attack is taking place roughly 107 degrees here, and of course 107 degrees here. But here you see the repulsive forces are there, and in that case there are no repulsive forces. So this will give you the major product, and this will give you the minor products. And with this diastereomer would form in the higher amount. Please remember this particular point. These two are energetically similar, and only the differentiation will arise out of the non-bonded interaction between the medium-sized group and the incoming nucleophile. Right? So this, whatever the repulsion will occur, this will occur due to this medium-sized group and the nucleophile. Here it will occur due to the small-sized group and the nucleophile. But of course, the repulsion would be less in that case. So this is the crude idea about that. Now you can, what we can do? We can apply this concept to the real molecule as well. So how we can apply this concept to the real molecule? Say this is your carbon and this is your hydrogen. I'm showing the stereochemistry of this as well. This is below the plane, and this is your phenyl group, which is above the plane, right? And this is your methyl group, which is this is on the plane. And here you see you are having this carbonyl group. Okay, and this is the CH3. I think there is no problem in that. Now what I am doing, I am changing my direction of the view. Right, this is my eye, and now I am looking at the molecule from this particular direction. See, in the earlier slide, you can see here from where actually I was looking from this particular direction and getting these two conformers. But in that case, I am looking to the opposite direction. So this will give you the different kinds of the conformer. right? But it looks different, right? But however, there is no difference, right? Only the viewing method is different in that case. So since I am viewing from this particular direction, now this carbon is the front carbon. This carbonyl carbon would become the front carbon. Okay. So I am drawing this. So this carbonyl carbon is the my front carbon, and of course this methyl is attached to this. So I am writing Me for this methyl. And this carbon will become the rear carbon, that will on the back side. Okay. And the backside carbon in the Newton precision formula will be shown by the circle. And then you see I am having my groups as well. So I am placing my groups according to the Felkin. So this is, you see, this is my largest group. Phenyl is much bigger than the other groups. And this is my medium sized group, methyl. And this is my smallest one. So what Felkin says that largest group would be placed at the right angles to the carbonyl plane. So this is basically your 90 degree. Okay. And then you are having other two groups. One is methyl and other one is your, say, hydrogen. So this is one carbon. And what we can do now, again we can we can fix the position of the front carbon and moving the rear carbon by 180 degrees. So this will come here, this will come down, and this will go up, backside carbon. Okay. Since I am rotating the backside carbon, it clearly indicates that the position of the front carbon is fixed, and this is my Me, and this is my rear carbon, and after 180 degrees rotation, my phenyl would come here, and my hydrogen would go there, and my methyl will come down like that. Okay. So these two conformer I am getting, which energetically these two are same, but the difference in the percentage of the diastereomers would come due to the interaction or repulsive interaction between the incoming nucleophile and the groups, whether it is medium or the small size group. Okay. So what I am doing here, say first in the first instance, my nucleophile is coming from here. And in that case, say my nucleophile is hydride ion, H negative. Okay. And this H negative is approaching onto this particular carbon. Okay. So before moving further, I want to tell you one thing. What we can do here, say I am having this particular compound, right? So what I can do here, I can react with this LAH, lithium, aluminum hydride, and after that I will do the protic workup. So when I do the protic workup, this O will become your alcohol. So your product would look like this actually. Not drawing the stereochemistry, H here, pH here, Me here, this would become OH, okay, and CH3 is already there, and you see one of the hydrogen is actually the nucleophile which is coming here. So this OH is basically we are forming by the protic workup, and this lithium aluminum hydride is giving this particular nucleophile, and you can clearly focus that this is your chiral carbon and this is your chiral carbon. This will form two isomers actually, and both will have the diastereomeric relationship, right? This is very, very important. I forgot to give the general reactions earlier, but in the CRAM'S I have explained the general reactions as well. Right, now I am doing my reaction here. So what I will do here, first of all, I'll react with this LAH, lithium aluminum hydride, which will give you this nucleophile, okay? And after that, I'll do the protic workup and I'll write the H positive for this one, protic workup. So what will happen, see, I'm explaining you, I am not disturbing my position of the rear carbon, okay? So what I am doing, I am drawing my rear carbon. See, this is my pH, which is present on the rear carbon, and this is my Me, which is present on the rear carbon, and this is my hydrogen, which is again present on my rear carbon. Okay, so I am not touching the rear positions, this one, and this one, because reaction is taking place on this front carbon, right? This carbonyl carbon reaction is taking place on this one. So hydride is coming here, so H will come like that only. So I am drawing my nucleophile, which is coming with the blue color. I have shown with this blue color. So with this carbon here at the center, my hydrogen will approach. Okay, and at the top you see this OH would be there, and of course, this is your methyl group. Again, I am explaining you for the newcomers actually. See, this is attaching here, so this will attach here like that. This is this one, and then this after protonation, this will become OH, so this will be pushed back here, like that, and this AB will come here. This is the most stable conformer. Okay, this is how you can get this structure. So this is one isomer which we are forming here, right? And mind you, you can understand this thing very well because this hydrogen is very small in size, and this hydride ion again is very small in size. So there is very little repulsive forces between the two. But in the second instead, if say I am allowing my nucleophile coming to different direction, right? Say for example, it is coming from here, say opposite to this one, and it is coming from here, nucleophile, right? So what will happen? Nucleophile means, nucleophile means my hydrogen, okay? It is coming like that. So there is repulsive forces between this methyl, which is medium sized, and on this one. So this will give you the product which would be in the lesser amount. So this is your major product. Please remember, this is your major product because the repulsion between the nucleophile and the smallest group hydrogen would be the very low. So again, I am not touching my rear carbon, placing my pH phenyl here, and my hydrogen here, and my Me here, and you see this hydrogen is coming here. So this is my hydrogen in the center, and this is my OH, and this is my Mg. So again, you can see here, this is approaching just like that. So this will form bond with this one, and now this will become OH. So this will be pushed gauche to this pH just like that, and this will come gauche to this one. So this is another isomer, and this isomer is the minor isomer. Okay, and mind you, please remember these two have diastereomeric relationships. Diastereomeric relationship. Please remember, they are the diastereomers. Okay, how you can see diastereomers? They have the different configuration at one carbon atom. Okay, and if you know how to give the configuration, RS configuration to this nuclear projection, then it is very fine. If you don't know how to give the configuration to these, then for this there is a way how we can give the configuration to these isomers, which I have discussed in case of the CRAM'S rule as well. But again, for newcomers, I am converting this I am giving the configuration to the chiral carbons for this particular major one, and then for minor one you can do by yourself. So what is the method? So you can take the snapshot of this one. I am removing certain things from here. First of all, I need to convert this into the Sohor's formula. Please remember, I need to convert into the Sohor's formula, but in this way it is little difficult. So what you can do, you can rotate whole molecule, right? You can rotate whole molecule to form Y of the front carbon. That means this actually, right? So this you have rotated just like that. Here you see, this you have rotated here. So this will come here, and this will go up, and see this H will come down. Please remember, okay? So I am putting my H here. There is no problem in that. Okay, there is no problem in that. I am putting my H here, and this is my Me, and this is my OH. There is no problem in that, right? Please see carefully. See this OH I have placed here. This Me is coming here, and this H is now coming down. So what I have done are Y only, Y shape only. Okay, this is very important. Now you are having this rear carbon as well. So you will have another Y in that case, but that Y would be the inverted one, just like that. This is inverted Y. You can put this inverted Y. This is the trick basically. Now what you can see, between OH and Me, your pH is placed. So what you can do, you can write pH here. There is no problem. Okay, and you can see this hydrogen right, is placed between the Me and the H. So it is quite easily you can put Me here and H here. And you can see the relationship. This Me and this Me, they are 180 degree. They are at the angle of the 180 degree. And again, you can see here they are at the 180 degree. Okay. And you see this Me and OH, they are at 60 degree angle. So Me and OH at 60 degree angle here. And this Me at OH again at 60 degree. So this is again this one. So this is another Newman prediction formula. And you can convert this Newman projection formula into the here Sohor's formula. So how we can convert this into the Sohor's formula? Now I am converting into the Sohor's. So this is my front carbon, which is this one. And this front carbon is having OH here. And this is having Me here. And this is my hydrogen here. Okay. And just in the rear position, this is my rear carbon, the back one, right? So this is now I have placed this rear carbon here. And this rear carbon is having this kind of the chemistry. This Me is placed here. And this you see in the rear carbon, hydrogen is placed here and pH is placed here, right? So I need some space. This is Sohor's. This is Sohor's formula. So I am converting it into the Fisher formula. But for the Fisher projection formula, you need two regular Y shape. This is, see, this is one Y and this is another Y. This is the trick actually. You need two Y shape. So this one Y shape is already there, which is this one. You can put OH here and you can put Me here and you can put OH here. Now you can rotate by rear carbon by 180 degrees. This pH will come down. Okay. So this is my rear carbon and pH is coming down. And similarly, by 180 degree rotation, this Me will go on the right hand side and H will come on the left hand side. Okay. Please remember. So this is your H and this is your Me. Now you can convert this into the Fisher formula. So in the Fisher formula, what you can do, this is your chiral carbon. Okay. This is your chiral carbon. Please remember. And this is again your chiral carbon. So basically this system is having two chiral carbon. So one chiral carbon is here, another chiral carbon is there. Okay. If you are looking your molecule from here, this hydrogen at the bottom place. Okay. So you can put this hydrogen here. And on the left hand side, your OH is there. You can write OH. And in the right hand side, you are having Ne. So you can put Ne here. And you see this pH and this H are anti to each other. Okay. So you can put this pH here. And on the left hand side of the pH, we are having Me. And on the right hand side, you are having the H. This is your Fisher formula. Okay. Now what you can do, you can very easily and conveniently write their names as well. Right. So this is your chiral center. I am giving the name to this one using the blue color. So this will get the priority number 1 because oxygen is having the highest atomic number. So for this, you need to know how to give R and S configuration to the compound. If you don't know how to do this nomenclature, again I am giving you the link in the description box. You can go there and learn from there as well. Okay. But I am telling you, say this is having the priority number 1. The above carbon will have the priority number 2. This is the priority number 3. This is the priority number 4. So 4 priorities are there. And you are moving from highest priority to the lowest priority. And by doing this, you are moving clockwise direction. That means this chiral carbon is having R configuration. This chiral carbon is having R configuration. Okay. Now, if you do the configuration for this one, so again what you can do, so see if this you have understood, I need some space, so I am removing my earlier rotations from here. You can take the snapshot. So this I have decided, this is having the R configuration. Okay. This carbon. Now, but what about this carbon? So this group, this entire group will have the priority number 1 according to the rules. This will have the priority number 2. This will have the priority number 3. So you are again coming in the clockwise direction, but your lowest priority group 4 is on the horizontal line. So you will reverse the configuration. Okay. So you will come here. It is coming clockwise direction, right? But lowest priority group is present on the horizontal line. So you will reverse the configuration. So this will become actually your S. So this system is having the configuration. This is R and this is S. Right? This is how you can do the things. But what you can do for this minor configuration, again you can follow the same procedure and you can get the configuration of the 2 carbons here. Then you will find what configuration would be R and other configuration in that case would also be R. Okay, or one would be S and other would also be S. So there will be the difference in the configuration only at one chiral center. That means you are having the diastereomers. You form the diastereomers, right? This you can check by your own and you will find. See, I am telling you this one will be the correct answer, not this one actually. You can do by your own. So this is how you can understand the Felkin Anh model, and this is very, very important. But here you can see another very important concept is there. What is written here? Effect of electronegativity in the Felkin Anh model. Effect of electronegativity in the Felkin Anh model. So what is that effect which this you need to understand. So what is written here? If electronegative atom or the group like halogen or your say methoxy or ethoxy or your NR2 groups are present on the alpha carbon atom, then this group would become equivalent to the largest group and would be better placed orthogonal to the plane of the carbonyl carbon. So now let us take a real example for this. Okay, type of the real example, we can understand how the electronegative group, if attached to the alpha carbon to the carbonyl, will orient itself orthogonal to the carbonyl group, right? So what is the example? Say first of all I am drawing this particular compound. Say this is my oxygen, and with this oxygen hydrogen is connected here. So I am taking aldehyde this time. Okay, please remember. And this is your rear carbon. Okay, and this rear carbon having 3 different kinds of the substitution, and one very important substitution is ONE. As I have discussed, any electronegative group or the group which is ONE or NR2 type of the group, right? So this will how this will orient itself with respect to the carbonyl plane. This is something very, very important you need to understand. And another one is the hydrogen. Okay, and then the pH is there. Okay, and if you consider the bulk or the size of the group, so this phenyl is the largest one, and this hydrogen is the smallest one, and this orthomethoxy is the medium one. But it due to its electronegative nature, this will be treated as the largest group. Okay, and when this will be treated as the largest group, so this will go orthogonal to the carbonyl plane. Okay, this you need to understand. So we can quickly draw the conformation, Newman conformation for this one. Okay, and this time say I am looking my molecule from this end. Okay, I am looking on to this particular carbon. So this carbonyl carbon is basically your front carbon in that case. If it is the front carbon, then I can quickly draw that front carbon like that. This is carbonyl carbon, and the hydrogen, because it is aldehyde, hydrogen is connected with this one. And with the white color, I am drawing my rear carbon, which in Newman projection, it is shown by the your circle. Okay, and then basically without the modification, right, if you don't consider that the electronegativity, then obviously this phenyl, which is the bulkiest one, must go to in that particular direction, and your OMe will orient like that only. Okay, and this is your hydrogen, right? And this you can quickly change. What you can do, you can hold the front carbon, and you can front carbon is generally shown by the dot. Okay, in the Newman projection formula. So that circle is basically the rear carbon, and you are rotating the rear carbon. Okay, so when you rotate the rear carbon, you will get another conformation of this one, and you do the 180-degree rotation of the rear carbon. Okay, 180-degree rotation. So when you do the 180-degree rotation, this pH will come here, OMe will come down, and H will go up. So we can quickly draw the another conformation for this one as well. So since I holded this front carbon as such, okay, and only rotated the rear carbon, which is this one, by 180-degree, so your phenyl will occupy this particular position. This I have explained you in my previous examples as well, and your hydrogen will come here, and your OMe will go down. This is without modification, right? If you don't consider the electronegativity, basically they are the most populated one, right? The population of these two conformers would be very, very high because they are very, very stable. Okay. But if you consider the reaction, nucleophilic addition reaction, so for the nucleophilic addition reaction, you need to change the conformation of this one. As I already told you, this OMe would be treated as a largest one and this will take the position of the OHE. So how we can draw the conformation for this one? Okay. So I am holding the front carbon as such. For example, say this is my oxygen and my hydrogen is going down. Okay. And with the white, my rear carbon is there. And now I am rotating this molecule, right? So what now? Now what we can do here? See, I have drawn this one. This is the rear carbon, and now I want to place this ONE at the angle of the 90 degree. That means this should come here. Okay, this should come here. When this will come here, what will happen actually? This hydrogen will move. Okay, and this will come somewhere here, and this OMe will go somewhere there. Okay. So how we can draw? This is my OMe, which I am placing here, right? And my hydrogen, of course, will move here. And of course, my pH will go there, right? So when you are doing the nucleophilic addition reaction, this is the most reactive conformer. And this OMe I have placed orthogonal to this carbonyl carbon. You know, now this is forming the 90 degree angle. This is the slight modification. And I'll give you the region as well why it is actually happening, right? But before doing this, before doing the reaction, what I can do, I can convert this one as well. This is your neck conformer. Now I want to place this OMe here. So this will come here, right? And your next loop will come down. This will go there and this will come down. Okay. In the rear carbon. So what you will have now with the blue color, I am fixing the position of the front carbon. And then this is my rear carbon, and now I have placed my OMe here. Okay, when I am placing the OMe here, obviously my H will move here, and then I am having my pH here, right? So this has moved here, this has moved here, and this has right here. So you have drawn the two conformer, and these two conformer, mind you, this conformer as well as this conformer, right? In these two conformer, your electronegative group are at 90 degree with respect to the plane of the carbonyl carbon, and these two are the most reactive one. Please remember, they are the most reactive towards nucleophilic addition reaction. So how we can do the reaction in that case? Say for example, I am having my nucleophile, right? So you can have any nucleophile. I am drawing say NU, or you can take another nucleophile. Say you may take your say C2H5O negative or any other thing, right? So, but right now I am generalizing it. Okay. So when I am generalizing it, so I am taking nucleophile here. So this nucleophile will attack onto this rear carbon. Okay, because this rear carbon, sorry, onto not this rear carbon. I'm sorry. So this nucleophile will attack on the carbonyl carbon, and mind you, this will be the Burgi-Dunist trajectory, that is 100 near about 107 degrees centigrade, right? And this will give you the product. Now it is quite obvious. You see, this nucleophile is here, and this hydrogen is here. You know the stability of these two are equivalent. The only interactions or the repulsive interaction which would be there because of this hydrogen and the incoming nucleophile. Now you think in another way, if you consider this one and you are attacking nucleophile from this end, right? Earlier one. So nucleophile is negatively charged and this oxygen is also having the lone pair. So there would be lots of repulsion, right? And due to this repulsion, the reaction will not occur. That's why I have placed this OMe onto this particular plane, because it is actually anti to this nucleophile and reaction is going very well. And this will give you the product. So what product it will give you, I am drawing here. Okay. So this is my say rear carbon, and the position of the rear carbon, the substituents of the rear carbon would be fixed because I am not doing any reaction on the rear carbons. Okay. So rear carbon hydrogen, rear carbon pH, and your rear carbon OMe will remain as such. and your nucleophile, which is adding on to the carbonyl carbon, is coming from this end, Nu. And you can see here, this nucleophile like basically is coming, so it should be in between the pH and H in the 2D drawing. So I have placed here. When this will happen, actually, this after protonation, see, protonation will also occur in that case. And after protonation, this carbonyl will be converted into the alcohol. So this alcohol will be pushed there. So you will write your OH here. Okay. And this is the hydrogen which will come here. This is the most, this will be the most stable conformation this per. So this is your hydrogen, right? So this product would be the major product. And now if you see in the second instance, say your nucleophile now is coming from this end. The nucleophile is coming from this end, approaching onto this carbonyl carbon to do the reaction. Okay. Now you can see here this nucleophile and this nucleophile will have the repulsion with this group. And you know this phenyl is quite bigger than this particular hydrogen. Then there would be some repulsion. So the excess of these carbonyl carbon to the for this nucleophile would be slightly difficult in that case. However, the reaction will occur, but it will occur with the slowest rate, and the product you get, that product would be actually is the minor one. So how we can draw? I am not touching the rear carbon, so the groups attached to the rear carbon will remain as such. Okay, and see, this is your hydrogen and this is your pH as well. And since you have added nucleophile from here, so I am using the blue color. So what you can do, this is your nucleophile Nu. Alcohol will convert into the, carbonyl will convert into the alcohol. This will come here and this is your hydrogen. So this is your another isomer and this would be the minor one. Now what you can do, see, this is your homework basically. What you can do, you can take any nucleophile and making this carbonyl carbon again a chiral center, because this is the pro-chiral center. See, earlier one I said that this is the pro-chiral center. No, it is not the pro-chiral center. I am sorry for that. This is basically the chiral center. This carbonyl carbon is the pro-chiral carbon, and pro-chiral carbon is the carbon which after the reaction converts into the chiral center. Okay. See, in the previous two examples, I actually repeatedly said that this is the pro-chiral carbon. I am sorry for that. This is not. This is the pro-chiral. Right? I'll make the correction there if possible for me while uploading the lecture. Okay. So what you can do, you can take this nucleophile as such and again make the two diastereomers, and then by following my idea of converting them into the Sohor's and then to the Fisher projection formula, you can assign the configuration to the two carbonyl carbons, two chiral carbons, as well as you can do here as well. Then you will find one of the chiral carbon will have the different configuration, and you know that by definition diastereomers are those isomers in which there occurs the change in the configuration at least at one carbon sector, which I have explained in the earlier lecture as well. So I think in the Felkin Anh model, if you understand these much of things, then this would be quite helpful for you. See, there may be some more other modifications as well, but I am not going into the detail of those one. And according to me, after the CRAM'S rule, this Felkin Anh model, up to this point, it is quite sufficient for the students who are studying in the MSc or who are CSIR net aspirants or the GATE aspirants. This much of information, I think, would be the helpful. I'm not saying that it is the complete one, but this must be this is helpful actually for the students. So guys, I hope you understood the lecture. Okay, if you understood the lecture, grasping the things and learning new things from tetrahedral chemistry classes, please like the video, watching video for the first time. Please subscribe the tetrahedral chemistry classes and do share with your friends as well. In the next class, I'll meet you another important stereochemistry concept, that is next rule. See, so far I have discussed the CRAM'S rule and Felkin Anh model. In the next class, I'll discuss the Prelog's rule. Okay, so that's it for today. Thank you very much.